Thank you again for the introduction. I would like to thank the organizers for inviting me to Marseille. So what I would like to talk about today is this result which we are working on. Well, this part is done, but as you will see, it's very much of a first part of a work, of a project which we are working on. And this is a project which is together with Alex Blumenthal, which is now in Maryland, and Zhang, who's in Toronto. And so let me give you first the main object of study of this work, and then I will try to do some kind of moral justification of why we are studying this map, and then I will hopefully give you an idea of the proof, which is actually the main point of this kind of work. So this work is kind of a proof of concept that something can be done, and hopefully we will manage to get more better results as we progress by this strategy. So the main object which we will consider is a map, which I will call G sub epsilon, as in any slow-fast system which one should take care of. There's an epsilon somewhere, so the map is a map from the cylinder to itself, which is a composition of two maps, which is, well, I will call S epsilon and T epsilon. And they are as follows. So T epsilon is a tilt. So let me draw a picture here. So I will have a horizontal line will be mapped to something like this by T epsilon. So T epsilon will map x, y to, or rather, let me call it Z for some reasons. X will be put, and Z goes to epsilon sine 2 pi x. And this is T of epsilon. It's T epsilon. This is a tilt, and then I have a shear, which I call S epsilon, and S epsilon makes Z stay put and twists the X coordinate in the following way: 1 plus alpha Z, and I will fix alpha positive. Well, I will allow alpha to be equal to 0 just for the introduction, but we don't have any result for alpha equal to 0. And so pictorially what happens is that if I have my cylinder here, I take a vertical line, and the vertical line will go to something which winds around the cylinder many, many times by S epsilon. So a vertical line will go to something like this. And by this scaling factor, I know that the intersection will happen on a lattice which is very tiny, epsilon to the 1 plus alpha Z. So this spacing is epsilon to the 1 plus alpha Z. And I'm taking the composition of these two functions, which, okay, fine, has a formula which I don't want to write at the moment. Of course, this is a composition of two area-preserving maps, therefore it's area-preserving. So G epsilon is area-preserving. And then, of course, it's an example of a slow-fast system, because I have a very slow, well, if epsilon is small, as we shall assume, I have a very small deformation in the Z variable, and then I have a very strong twist in the X variable. So this is an example of a slow-fast system, and what do we want to understand? We want to understand the behavior, the long-term behavior of random variables, which I will consider. So let me call X n epsilon and Z, and epsilon just the iterate of this map from x and y. And if I assume x and y to be uniformly distributed with respect to Lebesgue, for instance, because I have an area preserving transformation, then I want to understand the limit for large n in some scaling of the behavior of the slow variable. So I want to understand essentially what happens to z and epsilon. Well, of course, I need to remove the initial point. And this is just given by the sum n equal to 0 to big N. Let's call this big N minus 1 of sine 2 pi x and epsilon. So this is a Birkhoff sum of this function sine. And since Lebesgue is invariant measure here, one would possibly imagine that once you get some sort of averaging, going on, this will average to 0, so the net effect will be 0. So with net effect that we have to study is a diffusion. And therefore, the limit that we want to study is a diffusive limit, which is n going to infinity as epsilon to the minus 2. And in this limit, one would like to have some kind of convergence to some diffusion process. And I will give right away the statement of this result, which is what we prove. And as I mentioned, it's, it is very likely to be improved soonish, but for the moment, that's what we have. So the theorem that I want to present is the following. So one immediate remark is that as alpha becomes larger, the shear gets larger, and to some extent, this should help with averaging. Okay. And in fact, the result that we have is for alpha sufficiently large, and we need alpha bigger than 8. And hopefully, one of the main tasks of this talk is to give you an idea why 8 is equal to 8, and we cannot take 1 or 0. So, so let's take a alpha bigger than 8, and then I want to consider x, z, which are the initial conditions. I want to get some randomness in the system through initial conditions, so I want to take a random distribution of these things, which is a uniform distribution. And I want them to be uniformly distributed, say, in tau, in the torus times some interval. So I take a chunk of the cylinder, and then I throw in a random variable in there, which is uniformly distributed. And the result that we have is that z and epsilon, n now is fixed to be epsilon to the minus 2. And please don't let me write the integer parts here. Minus z, and this converges in distribution to, epsilon, as epsilon goes to 0, to what? Well, to a Gaussian distribution centered at 0, and sigma squared is equal to 1/2. Okay, so this is what I want to show. That's what we prove. And 1/2, observe, this is just the integral of sine squared. So that's the average of sine squared, which is this sigma squared. So that is what we want to show, and this is a theorem again, together with Blumenthal, myself, and Zhang, 18. And okay, so this is what we want to show. So I talked about what diffusion means in the title of this talk. I talk about so fast, and now I want to show you a connection with the standard map, which is pretty obvious. If you look at that picture, there's an obvious scaling that one should try. So the picture on the left, you see that you have a natural lattice which shows up on the cylinder, which has size epsilon to the 1 plus alpha z. And what if you normalize this to size 1? So if you normalize this to size 1, so you define y to be, so this is a normalization or change of coordinate if you want. So y is now epsilon to the minus 1 plus alpha z. So you rescale this, you amplify the z direction, and you call it y. So this change of variable conjugates g epsilon to the following map, which is the standard map. So FL of xy maps to x plus y plus L sine 2 pi x, comma y plus L sine 2 pi x. And here L is equal to epsilon to the minus alpha. So this is a standard map of parameter L, which is a very well-known error-preserving analytic symplectomorphism of the two torus. And I'm having a parameter which is epsilon to the minus alpha, so a very large parameter. So we are in the regime which most people, myself included, believe should be somehow a diffusive regime. And in this setting, if you now take L as a parameter as opposed to epsilon, then we would have that N should grow as 2 divided by alpha. So this is the renormalized picture for the standard map. And so we will get, in fact, this theorem over there. There's this shadow. This theorem over there will be obtained by means of an analogous theorem for the standard map, but it is a very strange looking theorem because, well, let me state it first. So now I have a uniform distribution of my initial conditions on the two torus. And I consider, well, let me state the epsilon more, well, not epsilon, delta more general statement of this above here. So let phi, I want to consider phi to be an observable, which is an observable of the x variable only. So I'm just going to consider a function from T1 to R. And for simplicity, I want just to consider it to be a C1 function. I will comment in a second about this. And then I want it to be zero average. So the integral of phi is equal to 0. And not identically 0. Then let n to be a function of the parameter, which is a small o of L to power 1 over 4. This 4 is related to that 8 by this formula. And then what we have is that if you renormalize the Birkhoff sum to the I of xy, I from, say, 1 to n, well, okay, 0, n minus 1, and then I divide by n of L to the minus 1/2. So I take this. This converges to the normal distribution centered at 0 of sigma squared equal to the integral of phi squared. So that is again in distribution as L goes to infinity. So we have a limit theorem for the standard map, which you can read off in various ways. So here the parameter is going to infinity, and as the parameter is going to infinity, you're allowed to take longer chunks of iterates. And the length of the iterates which are allowed to take has to grow slowly with respect to the parameter. Okay? So the smaller the alpha, the faster you would be allowed to grow. And if alpha were equal to 0, then we would have a central limit theorem for the standard map, which would be fantastic. But of course, this is not the case because we have now alpha bigger than 8. And another comment that I want to do is that, of course, you would be able to state something for Holder observables. So if you want, you can put here, well, alpha is already taken, so I want to take C betas, if you want, Holder. And then here you would need to get an even slower growth. So you would have to have a growth which is small o of L to the 1/4 beta. Okay, so that is just a usual trick of modification. So there's really nothing added into the mix by considering Holder observables, but in principle one could state a slightly more general result as such. So that's actually what I want to show today. And this, I guess I don't need to explain. I mean, you can see how these two things relate to each other. Okay? So that is for the statement of our result. Any questions so far? Good. So what I would like to spend a few minutes on is now a kind of motivation for this kind of system. So the motivation comes from a monograph by Dima, which is now 12 years old, I guess. It's a repulsion from resonances monograph, which some of you might know. And essentially, the motivation, so I be deliberately very vague and quick in this part, because again, it's just a motivation, but hopefully I would like to convey that this is not completely unreasonable system to study. So the motivation is averaging of nearly integrable system for quasi-periodic fast motions in the presence of resonances. So what do I need? What I want to do? I want to consider a system which I will write as follows. We have an action coordinate which is driven by some function fi phi theta and depends on a parameter epsilon. I have an angle coordinate which is driven by another function which depends on these guys. And theta is just a fast object which evolves, say, with epsilon to the -2, some omega. And for simplicity, let me take omega just depend on I and phi, but one can do some more sophisticated things. So this is just some system which is driven by a fast rotation. Okay, omega gives just a rotation of theta. And then, of course, one would like to average this system. And of course, you're only allowed to average when you actually have a rotation. So you're only allowed to average when omega is not 0. So if omega is not equal to 0, you're allowed to average. And what averaging would say? So this is just a rotation. So what I would need to do, I would need to study the average system, which is given by integrating these guys with respect to theta. So the average system, let me call it I bar and phi bar, would be driven by the ODEs, which are just, this is given by the integral of f with respect to theta, and this would be given the integral of g with respect to theta. And I assume this guy to be completely integrable. So if this is completely integrable, it means that this wouldn't change. So I am requiring that the complete integrability of the average system, and this would be something like P of I, where P is a momentum. Okay? So what is the picture for the average system? The picture for the average system, again, is a cylinder. And then you have I here is a so-called I bar, if you want, well, is an adiabatic invariant of the system. And on each of these things which are preserved, you have some rotation by some P of I. And if you have some non-degeneracy assumption, then you will have a twist, actually. So maybe P is increasing in this region, and so as you go up, you will rotate with a stronger speed. But then, of course, I told you that I'm allowed to average only when omega is not equal to 0. So what happens when I have a resonance, which is omega is equal to 0? Well, omega is equal to 0 is really something which depends on where I am on the cylinder, so I am phi. So let me assume by some kind of non-degeneracy assumption that this curve here is transversal to this foliation. So I will get some curve like this. And then let's see what could happen. So outside of the region close to the resonance, averaging makes perfect sense. So I'm happily rotating around my cylinder with speed P of I in the average system. But then, of course, here averaging phase. So we need to see exactly what happens. So let me blow up this picture and draw it on this side of this board. So now what I want to see. So averaging is not allowed anymore close to here because theta stops. So I actually need to see what happens in the theta direction. And so I can do some rescaling. Again, I don't want to be any more precise than just drawing pictures. But I can do some rescaling. And I can see what happens in some renormalized coordinates. So I need to rescale both space and time to an intermediate time scale, which is epsilon. So if you notice over there, there's epsilon squared, which doesn't make much sense on its own. But in fact, it's there to underline the fact that there are actually two time scales in this system, which we will use in the averaging. So one is the very slow time scale, which gives this averaging, and then there is an intermediate time scale which will be used here. So this is averaging with rate epsilon, and this is averaging with rate epsilon squared. So over here, what happens is essentially the following thing. So you have, I want you to think of this as the phi direction or some renormalized phi direction, and since they have this transversality, phi is essentially parameterized by omega. So this is going to be the resonance line. And then I need to see what happens in the phi, in the theta direction. So, so the theta direction will be this direction. And as it turns out, you can do this averaging, and you will find that the dynamics, once you enter this resonance region, is given by, again, by averaging by a Hamiltonian system. And the Hamiltonian for the system depends on I. And again, let me write these things in a very sloppy way, but phi and theta. And essentially what you get is some rescaling of phi squared over 2. And then you have a parameter, sorry, you have a potential which depends on I, and theta. So what's the point here? I have this trajectory which is coming from the non-resonant region, and this trajectory is rotating very, very fast in the theta direction because of the fact that we are outside of the resonant region. So far away from resonance, I will have something like this picture. And then I get into the resonant region, and then the dynamics of phi and theta satisfy this equation. So there are actually two possibilities for V. One is that if you look at, for fixed I, if you look at what happens in theta, you have actually a critical point. So you have something like this. And the second possibility is that you don't have any critical point. So this case is what is called to be a strong resonance. And this is a weak resonance. So in the case of a strong resonance, if you picture what is the phase portrait of the potential over here, you will find that there are separatrices which correspond to this level of the potential. And the separatrices look like this, for instance, or maybe the other way around, but let's not worry too much about this. So what could possibly happen in this picture for strong resonances is that you have, again, this is just an average picture, so this separatrix is not really there. It just tells you what should happen in the limit, but of course epsilon is non-zero, so you might have something like this happening. So this thing comes rotating very fast and then can go around this globe, or it can actually get inside and stick inside for a while. And if you stick inside for a while, it means that theta is fixed in some special point. Phi is also fixed in some special point. And so if you look at what happens in this scale, you would actually have that this is traveling along the resonance line for a bit until this potential, which depends on I, changes, and the trajectory is spit out from this globe, this thing, and go back going around this cylinder. So in the case of a strong resonance, what could happen is that the trajectory would actually walk for random time over here and then be spit out at some point later on. Okay? And more interestingly, what happens in the non-capture region is that, well, this thing has, again, some flux which should be preserved, and you have a very tiny region of trajectories which are captured, and the rest should compensate for this fact. And so the net effect is that the other trajectory, the one that are not captured, will be somewhat pushed in the opposite direction. And this is exactly what repulsion for resonances is, and that's the content of Dima's monograph. And so what he proves is that in this case, you can average, you get a net averaging out of this system that will push most of the non-captured trajectories away in a definite direction. Okay? And so he does averaging, and he does averaging in this setting, and then he finds out limit theorems in this sense. And this was fine. But then what happens if you don't have any of these things? Then you just have a weak resonance, and a weak resonance means there is no such a separatrix. And essentially, the situation is like that. So you just have a turn back, that things turn back quite quickly without spending too much time close to the resonance. And so what does this mean? It means that how long will be this time? Well, it be approximately epsilon long that you make this turn. And in this time, I will change a little bit, because here, of course, you're not mixing at any rate. And so you will spend an epsilon time close to a given point over here in theta and phi, and so I will vary with some value, which is whatever f of I, theta, and phi is in this specific point. So f will modify I by a factor epsilon, and let's see how this is distributed with respect to phi. And of course, there is no preferred phi here, so the distribution would be essentially uniform. So what this says that there is a tilt in I, which is a zero average, and of size epsilon. So that's exactly what that map is trying to capture. So you have a shear, which is what happens when you go around the cylinder, and each time you cross the resonance line, you will get kicked up or down by a factor, by something amount of epsilon, and this amount will average to zero, because in the case of weak resonances, there is no preferred direction. There's no preferred point in which the resonance system can linger for a very long time. Okay? So essentially, this is a justification in this setting of weak resonances of this map. And of course, this is easier to study than that, because over here you just need to get averaging results on a time scale which is epsilon inverse. And over here, in order to see anything, you need to wait for diffusion time scale, so you get epsilon to the minus 2. Okay? So in this sense, the case of our interest is more complicated than what Dima was working on in this case, but of course we have much weaker results for the time being. So that's just to justify my model up there. Okay? So this is, again, a motivating example. So one thing that I should mention is that in this case, if one would have to, well, this model would give a very specific alpha in this setting, and the alpha that it would give is 1. So, okay, we are still also very far away to prove anything in this model, but at the very least, we have the structure there. So I should say that this would give a dynamics which is g epsilon with alpha equal to 1 in the weak resonance regime. Okay? So hopefully I motivated you enough to have a look at this map. And now what I would like to do, I would like to give some hints about the proof of this limit theorem. Are there any questions so far? Okay, good. So the proof of these results is, of course, a blend of dynamical and probabilistic techniques. And you can put your dividing line wherever you like most. It's actually, of course, not that well defined, where the dynamics ends and where the probability starts. So I will try to do that in a very artificial way, but hopefully that would give, I mean, again, the main purpose of this talk is to kind of advertise some way to deal with non-uniform hyperbolicity, which could be useful in other settings. So again, the proof would be, well, again, not very sharply cut, but divided into a dynamical part and a probabilistic part. So the dynamical part is the study of essentially the standard map with fixed parameter L. So in the dynamical part, we will fix L to be some large parameter. And let me stress that this is very large. And then what do we want to do? Well, the idea is that we want to construct a filtration, which is a dynamical adapted filtration let me call it Fi. Well, I'm cheating a little bit, but okay, no, let me not cheat that much. So this filtration will depend on the dynamics, and the dynamics depends very, very strongly on the parameter. So each element of this filtration will depend on L. So that's what it is. And this filtration, of course, is a filtration with sigma algebras, which are called sub-sigma algebra of Borel, for instance. And then what do we want to do? We want to study the Birkhoff sum of this map from, say, 0 to n minus 1. And let me give this guy a name, Birkhoff sum n L of phi. That's a definition. And then what I want to do, using this filtration, I want to go on this other side of the board and actually study some other guy, which is just the conditional expectation of these guys with respect to the filtration that I just constructed. So I will, make sure I get all my indices right. So I get the conditional expectation of phi after f L I minus 1 with respect to f I. And then, of course, these are two different functions. And what I need to ensure that they are not too far away. And in fact, what we need to show is a lemma which says that if I take S and L of phi, and if I take S tilde and L of phi, well, their difference is not large enough in the sense that if I obtain a limit theorem for this guy, I will obtain a limit theorem for that guy. So I just need to make sure that this is small o of whatever I'm normalizing with. So n L to the 1/2, or minus 1/2. No, 1/2. So I want this to be small o of whatever I'm normalizing it. Therefore, in the limit, if I prove a central limit theorem for this guy, I would obtain the central limit theorem for the dynamical guy. And then, of course, then there's a combinatorial probabilistic machinery that starts to get in. So this, you can rewrite it as, in fact, a martingale difference sequence. So you can rewrite this as sum of some guy u I, and which depend on n or depend on L if you want, of L. And this is a martingale difference and then what you do, yes, is a relatively standard relatively standard business, because once you have such a thing, it's not impossible to guess that you are able to prove a CLT for this thing by means of kind of standard techniques in probability, and that's in fact the case. But this is, at least to me, it's a rather exotic limit theorem, because if you have a look at what we are trying to do, we are sending the parameter to infinity, and as we send the parameter to infinity, the filtration would change. So we need an array limit, kind of array limit theorem, and this, unless you guys, any of you has any better reference, would follow from a theorem of McLeish, which says that, okay, I'm just going to write a statement. If you have a probability space and you have an increasing sequence of numbers, a sequence of filtrations f1n, f2n, up to fkn, n, which are all subsets of f, and you have a martical difference sequence which satisfies a number of assumptions, so I'm going to write them down just for completeness. So the maximum over I in 0 up to kn of the absolute value of xin is uniformly bounded in L2. And then 2, I have that this same thing goes to 0 in probability. And then I have some normalization, if you want, which is 3. 3, it is that the sum up to kn of these guys converge as n goes to infinity to 1 in probability. Then you have a CLT for these guys in the sense that the sum up to kn of xin converge to the normal distribution. And then you apply this framework to some renormalized version of this martical difference and blah, blah, blah. So this is not the part I would like to focus on, because, again, I want to convey some dynamical construction. So again, part of the game here is to check 1, 2, 3, and then conclude that there is a CLT for S tilde, which gives a CLT for S. Yes, so it should be squared, I guess. There should be a square somewhere, yes. Okay, so what do I need to do, and why is this at all relevant for non-uniform hyperbolic systems? So let me give you a hint. I would like to, well, let's erase this board. So the first thing that you want to do is to put your standard map in a reasonable form. So you change variable once again. This is a canonical change of variables, which is xy goes to, say, x minus y. And then fl, in these coordinates, I will abuse notation and call it fl again. I'm already abusing notation by calling this guy x and y again, so you wouldn't really notice what I'm doing. So xy is 2x minus y plus L sine 2 pi x, and this is just x. All right, so what is the feature of this map? So I'm just going to draw a picture. So for very large parameters, what happens is the following. This map is essentially hyperbolic unless you get into a region which is a bad region. And the bad region is close to the critical points of this function over here, the x variable. The reason for that is that, of course, if you have I mean, if you compute the differential, you will see there is a strong expansion in the x direction unless when this is a critical point, because the expansion is driven by this large parameter L. And so what one could do is to consider critical set, which are two strips of size, I will introduce a parameter, eta positive, and actually I will get eta between 0 and 1. And in a bit, I will fix it to be 1/4 or 1/2. So I will get some strips which are of length L to the eta minus 1 around the critical points of sine. And let me call this the critical set eta. So S eta is the critical set of parameter eta. And what it is true is that outside of this set, outside of Sn, I can define a cone field which is just given by the vectors in R2, which are essentially horizontal, so that V is less than, I don't know, 1/2 U, 1/10, something like that. U. Did I get it wrong? Yes. No, I got it right. So I take some almost horizontal cone field, and what I'm saying is that if you take this cone field outside of the critical set, then it will be mapped inside of the same cone field in the image. So there is invariant of this set. So this is invariant. And of course, as soon as you cross this is completely butchered because you are turning around. You have all these kind of nasty things which happen in a standard map. But outside of this set, we have good properties. And then what we want to do, of course, we want to use standard pairs because that's the tool that that's the only tool that I can use to prove any kind of limit theorem. Well, that's not completely correct, but for this, in this setting, it is. So I have standard pairs. And what are standard pairs? Standard pairs are a pair, okay, of two objects. One is a curve, which is tangent to C. So C is defined everywhere. It's just a cone. It's a constant cone field. And it happens to be invariant only in some region of the phase space, but that's life. So C is defined everywhere, so this is a notion which applies to any curve. So I can take a curve which is tangent to C, which means that the tangent vector is inside of C. And also these curves are usually called U curves, maybe by Dima and other. And then I have, so this is a curve which is tangent to C, which is not too long. So the length of gamma is at most 1, so it will turn only once around the torus. And I also want that the length of gamma is strictly larger than some O1 number, which I call delta. So these curves are not too large and not too short. And on top of it, I also need some bound on curvature, which are not very important for the moment, but I want to write them down because this is the definition, so bounds on the curvature. So this is the first ingredient, a curve. And then I have a density, so rho is a density on gamma, and the density has the property that if you take the logarithmic derivative of rho, this is bounded by a constant. So if this happens, I call this a standard pair. And then I need to define a notion of a sub-standard pair. In which some of these things are relaxed. And essentially, I will relax two things. The first thing that I will relax is this. And I will assume that gamma is maybe not larger than delta, but is larger at least at L to some negative power, and smaller than delta. And I want to make sure that gamma is not in the bad set. And I also allow my density to be a little bit wilder than what it was before. I allow this logarithmic derivative to be less than some constant times L to a positive power. Okay? So I'm relaxing a little bit the definition of standard pair, and I call this a substandard pair. And now the game is to understand exactly what happens when you iterate standard pairs in this map. And actually, I would probably need a big board, so I will use this. And that's going to be the last board of this talk, because it's 4 minutes to go. So I'm going to draw a picture. So I have my torus, and I have my critical set. And let me take a very long, a standard pair which is as long as possible, something like this. So it's almost horizontal. So I push it forward by the dynamics, and what I get, so outside of the red regions, I have enormous expansion. Actually, I have an expansion which is essentially L to the 1/2, say, if I consider eta to be 1/2. So let's take S 1/2 here, and then I will obtain a very strongly expanding map outside of this guy, and so in particular, very tiny pieces will be expanded to a full length. So part of this image is given by full length standard pairs, and I call these fully crossing standard pairs. And then, of course, when you approach this thing, you need to cut at some point, and then we end up with something which is a little bit shorter than a fully crossing part, and so I will draw them in yellow. So yeah, you have some parts which are standard but not fully crossing. And then you can get a little bit inside the critical set and obtain, now I'm going to use blue. Well, let me use green, which is almost yellow. I'm going to use blue because it's recycling color, at least in Canada, but okay. Then you have a little bit of an image, which is when you get a little bit inside the critical set. And these things are going to be substandard. But if I take an image of something which is too deep in the critical set, I will end up with garbage, because I will end up with something which is not even in a cone. So this I will call garbage, and I don't want to consider it. So most of the part of our work is to estimate the mass of things which get into these bins. So the mass of this is essentially O1. The mass of substandard pairs is essentially L to the minus 1/2. And the mass of the garbage is L to minus 3/4. And then what you do, okay, fine. Let's see if I can salvage some part of these substandard pairs. And so what you do, you take a substandard pair, something which is short, it's not very nice, but not terribly bad. And it's not in the critical set. So if it is not in the critical set, I will have enormous expansion, and everything, life will be good again after a while. So this is a recycling process. So if I have a substandard pair, this will be mapped to a very long curve, which is standard. And then again, I will, I can essentially throw away whatever I don't like that much. So the image of a substandard pair, so substandard will map to standard, and I have garbage again. So you have a part of the recycling guys which cannot be recycled, and you throw them in garbage. Okay, and again, part of the game is to estimate these masses, and this will be O1, and this will be OL to the minus 1/2. And essentially, here's the game. So you take a standard pair, you push it forward, you obtain these things, and you don't throw away anything except this garbage at each step, and everything you can recycle, you recycle using this. So at the end of the day, what you get when you iterate up and is a big chunk of mass which is O1, which is standard, a chunk of mass which is L to the minus 1/2, which is substandard, and a chunk of mass which is N, which is the number of times you iterate it, times L to the minus 3/4, which is garbage. Okay? So iterate n times and you get this decomposition. Now, as you might imagine, you have good equidistribution properties on standard pairs and not so good on substandard and garbage. And therefore, we get the following result, which essentially concludes this talk. So if by this decomposition and these estimates, we get the following thing. You take we want to estimate this object, which is how big is the iterate of your observable when you iterate along a standard pair, and you obtain something which is 0 at the leading order because this is 0 average, and then you have an error, and the error is bounded by the C1 norm of phi times n L to the minus 3/4 plus L to the minus 1/2. So if n is not too large, so in particular if n is a small o or big O if you want, of 1/4, this thing would be optimized, then you get L to the minus 1/2, which is what guarantees 1, 2, and 3 in McLeish theorem. Well, this part I didn't show you, but you should kind of believe me that n to the minus 1/2 is what you need to get McLeish running. And so this recycling scheme essentially tells you that you can push your equidistribution up to L to the 1/4. And that's why we have this funky requirement up there. And then of course, if one could say about your recycling very badly, you could do something better. And of course, if you do something better, you have a finite decomposition, and we could get better results. And that's what we are trying to do. I will stop here.
Thank you. Are there any questions or comments? Please wait for the microphone if you have a... Yes?
So your alpha is larger than 8. How far can you hope to decrease it?
So I guess the first step, so there's two things actually which matter. The first one is that we take an observable which only depends on the x direction. So your question has actually two answers. One is, if we keep that, I guess we can get down to 2 or to 4 by kind of implementing something at this level. But far more interesting would be to understand what happens if you have an actual observable of the torus. And that is actually the direction in which you're pushing now. So in this direction, already obtaining something with alpha equal to 16 or anything would be very nice, and we haven't anything yet. But I guess, I mean, if you really want to focus on observable which only depend on the fast component, then we can get down to maybe 4 or 2, for sure not to 0. 0 is completely out of our scope. But at least, I mean, some better managing of these bad parts could lead to some improvements down the road.
More questions?
So where do...
Please, wait for the microphone.
Or he can use my mic.
No. Okay. No, I'm just asking, in your picture, where
yes.
do the substandard pairs appear in the iteration?
So they would be, so the preimage of this blue part would be when you get a little bit inside here. You are breaking the condition of being standard, but not breaking the condition of being substandard. So you can get in a little bit a critical set up to a certain point. And that will give you substandard pairs. Okay? And of course, you can get too deep, otherwise you will get hooks, and then it's completely gone. But of course, I mean, there is some hope, at least this paper of Alex, there is some hope that one can do a slightly different thing. Rather than starting from a standard pair, you can foliate a box with standard pairs, and then you do the same thing, but when you get into the hook, well, you're completely screwed because there's no hope you can understand what's going on. But if you have a foliation, now you actually have a foliation with this kind of curse, and you forget everything, you erase these curves and you refoliate by some nice curves, then you keep going. So this is actually probably a nicer idea to deal with the garbage business, because at some point you completely disintegrate it and put it back in, rather than trying to recycle it as the same thing. You essentially put it into some machine which destroys it completely and packs it up back in a nice way. And this could be actually a nice solution to dealing with the garbage. Garbage will always be there. At some point you might hit elliptic islands, and then this is completely garbage. There's no hyperbolicity there. So you need some way to deal with garbage, and this might be some way to do it. So.
Yes, please.
It seems that you start with a nice initial distribution. What if your initial distribution is really on the right? I mean, very, very close to the right region. You start with right.
Okay, but then you expand once and you get a bunch of...
But you start with the right and then...
something really inside the red? Well, okay, yes, you're right. If you start really inside the critical set, then you can actually be supported, say, on an elliptic island. And so no...
Or maybe a little bit stretched out and then...
Maybe a little bit stretched out and then it's a complete mess, because you get a part which never will escape the elliptic island and the other part which will be stretched. So yes, we actually need some length, and that's actually why we take this. No? We start from a standard pair, because then we assume that if you intersect this elliptic island, the intersection will be small compared to the mass of this thing. And essentially, this is all in the garbage. So you might cross an elliptic island, but you throw it away as soon as you cross it. So you don't know. I mean, that's of course, you cannot push this too far, because elliptic islands have some area, and you cannot throw them away. But they are invariant, so if you start outside, you keep outside, and so in some sense, this shouldn't count, but of course, this is the problem of standard maps. So nobody really knows how to deal with it.
Any other questions? Okay, so before the coffee break, we are going to thank the speaker again, and the next talk is at 10:30.